Good morning, everyone. Happy Monday. How's everyone doing today? Hope everyone's doing well. So, a couple of announcements before we get started. Also, if you're in the chat, just say hello. Let me know if you have any questions. So, a couple of things. So, we'll be starting lab this week. So, lab 1 is this week. Make sure you're enrolled in a lab. So, everyone should be enrolled in both the lecture and a lab. So, if you're not doing the in-person lab with me, then you should be enrolled in the online lab section. And so currently I'm still uploading the video. That should be up later today. So video. So keep an eye out for that if you're completing this online. And like I mentioned previously, so lab 1 is the soap making. And so you could do this at home too. So if you are doing it online, all these components are kind of household ingredients minus a sodium hydroxide, but you could buy that from a craft store, Amazon, and do this all yourself. So any questions before we get started? And so the other thing is, so labs are turned in through Gradescope, which is just an external grading organization. So make sure you've joined Gradescope. There, you should have received an email with the class code. If not, just email me. Let me know. We'll get that sorted. So that'll be how you turn in the labs, but I do accept paper copies and emails. All right. Any questions or other comments before we sort of dive into lecture? So now let's kind of really start organic chemistry. So the second course of this GOB series is, of course, devoted to organic chemistry. So first of all, well, what is organic chemistry? If you have thoughts or examples or applications of organic chemistry, just post them in the chat. Organic chemistry is the study of molecules that contain carbon. And so you may be asking yourselves, why do we have a whole branch of chemistry devoted to, one element on the periodic table? So we have carbon here, so we're just focusing on carbon. And well, we find that carbon is pretty cool. And we'll go into why carbon is unique. But basically, all these organic compounds are carbon-based. So a lot of these that you use on a daily basis. So this could be paper, nail polish, your candles. There are synthetic fabrics like nylon. You can actually make nylon. What's the big thing missing here? Where's my cursor? So in this list, we're also missing pharmaceuticals. Can't spell. But all drug development, all that is going to be carbon-based. I mean, there are so many drugs, not even going to begin to name them. And then also fertilizers, or catalysts, other compounds can be organometallic base. So a ton of other substances, cleaners, can be organic base. So plenty of examples. We could go on and on and on with examples. And feel free to list any in the chat. So let's do a quick warm up here. So inorganic or organic. So remember, organic is just, does it have carbon in it? And so let's look at these three examples. So we have KOH, potassium hydroxide. Is that considered inorganic, organic? We have this formate, CH2O. Is that organic, inorganic? And titanium oxide, so organic, inorganic. Give everyone just a few seconds to kind of think in their mind. All right, so looking at this, we're just following a simple definition. So does it contain carbon? So this first one, potassium hydroxide. So no, so that's just an inorganic compound. What about this next one? So CH2O. So we have a carbon in there, so that would be considered organic. And then the last one, titanium dioxide. So no carbon in it, so I would write inorganic. Now that being said, I just want to emphasize that it's not always a clear-cut line, and you do have kind of a whole field called organometallic chemistry, which is kind of the combination of metals plus organic compounds. So let's look into, well, what really makes carbon special? Why are we focusing on carbon? Why are we carbon-based life forms? And so this isn't in the text. At least I don't think it mentions this. But carbon, we may have touched on it in this first quarter, but we're going to review. So carbon is smaller than anticipated. And so that just means based off of our periodic trends, if you kind of remember, our radius decreases as we go across the periodic table and we fill in those shells. But then we find just our estimated, what we would expect the radius of carbon to be is actually, the true radius is actually smaller. And so that leads to a lot of the interesting properties of carbon. So why we're also carbon-based life forms is so carbon likes to make 4 bonds. So it can bond with 4 different substituents. It can bond with itself. Carbon can also make single, double, and triple bonds. And we'll look at what that means. And so not only can it make, single, double, and triple bonds, for example, with like oxygen or, nitrogen. So it can make nitrogen, but it can also double bond, with itself. And so this is kind of carbon. We'll look at the geometries that carbon likes to take. But if carbon is kind of bonded to 4 substituents, then we find that it tends to make this tetrahedral geometry. So again, carbon with 4 atoms on it. So we want to write tetrahedral. So notice that shape of tetrahedral. And so because it's tetrahedral, it's all evenly spaced, so as far apart as they can. And so our bond angles on that are 109.5. 0.5. So something I want to point out. So I have my molecule kit here today. So I would suggest that you might want to invest in one. This is the one that I use. You don't have to buy this one. There's, other kits out there. You can always email me for advice, because this is more like a general chemistry kit, but some of you may prefer like a organic chemistry kit, and they're kind of different in what they show and what they can do. But I wanted to get this kit out so we could look at our geometry. And so our black balls represent carbon. My kit's all scrambled. And so those white balls represent my hydrogen. So I'm just drawing our tetrahedral structure out, just so we can see by model. And of course, the way this molecule kit works is we have our black ball for carbon, and it is what we call sp3 hybridized, and that it has our four holes ready. And so that's something else that we'll look into. So let's write this down: sp3 hybridized. So there's my methane right there. So looking back at this sp3 hybridized, I just want to write what this means. So this essentially means that we have an s orbital. Plus notice we have p3. So this means we have 3 p orbitals. So px, py, pz. Of course, those kind of look like this. And so they combine together to make this overall looking shape with our 4 lobes that are able to bond with those hydrogens. So let's look at the types of bonds. So we mentioned that carbon is unique, that it can make single, double, triple bonds with itself. So this is ethane here. So first, and let's practice some naming. So over here, this is called methane. So methane is for 1 carbon. Ethane, now we have 2 carbons. And so this is just our simple structure. So notice again, carbon makes 4 bonds. So we've completed and filled in those hydrogens here. So that carbon, right, we have 1 bond to carbon, and then the remaining 3 bonds have to be the hydrogen. So now looking over at this double bond, so we have, this is now ethene with this ene, meaning our double bond here. And so now this is stronger, so we have single, double, and triple. So single bonds, of course, are going to be the weakest and longest. And then generally, as you add more bonds, so all this means, right, is we're sharing more electrons. So now double. So they're sharing 2 pairs of electrons. So 4 total that they're sharing. And so the other thing to note is there is not rotation. around that bond. And to kind of show you how the model kits show that, so let's go back to our webcam. So with my kit that I'm using, you have these slightly longer ones, and these are for double bonds. And so what you do, I have my one double bond there, and then you kind of have to bend them. And so just as an aside, all right, this kit would have a hard time showing triple bonds, at least from what I have. You could fill up another circle, but you can kind of see those two bonds. But then the important thing is you no longer have that free rotation. So look, right, you can't rotate. Versus comparing with a single bond. And so now I could rotate that. So see how that freely rotates? And so that gives you a good representation of kind of the characteristics and why that double bond is important. Because now we're going to see that you can't just freely rotate about that. That's going to give you different isomers, different conformations, or there's going to be some sort of barrier to rotation that is measurable. Maybe you can heat it up, and then you would see, you know, that fluxional behavior. And then so last one here. So this is acetylene. And so now this is a triple bond. So of course triple bonds are going to be the strongest and shortest. And so now they're sharing, of course, 6 electrons, 3 pairs of electrons. So 3 pairs of electrons, 6 total. And then once again, so carbon always has to make 4 bonds. So it has 1, 2, 3 to another carbon, and then that last one is of course bonded to hydrogen. So we have all sorts of different isomers too. So the first one that your book kind of introduces you to are what's called these structural isomers. And so structural isomers, you know, just means that you have different shapes. So this is propane. So propane now meaning we have 3 carbons. So this is just in a line. Now looking at this one, this is kind of in a triangle, all bonded together. And so this would be called cyclopropane since it's, you know, in a little circle. Okay, so 3 carbons, that gives us our propane there. And then, so just notice the difference in formulas. So with this one, we have no what's called degrees of saturation, meaning we have no double bonds and we have no circles. And so we can look at our formula. So C3, H1, 2, 3, 4, 5, 6, 7, 8. So H8 versus a formula for this one. So C3H 1, 2, 3, 4, 5, 6. Oops, I'm so sorry. I was on the wrong. So there's our cyclopropane. So I'll give everyone a second to look at that. And so that's kind of the interesting thing too about organic chemistry. There's a lot of ways that they can be connected together. Let's look at some other isomers. So other things you can have, so these are just different, I wouldn't even call these isomers. So these are just different structures, but you do have these isomers. And so one example are going to be hexanes. So hexanes are sold as a mixture of hexanes. And so you have N-hexane. And so hexane means 6. So 1, 2, 3, 4, 5, 6. And so notice how we draw this. So you're going to want to sort of get familiar with this chemistry shorthand. And so how I drew this is, so every point here represents a carbon. So I have 1, 2, 3, 4, 5, 6 carbons there to go with my hexane. We could rewrite this. So another way to draw this, there's a lot of different ways. So we could, just draw this very explicitly. 1, 2, 3, 4, 5, 6. And then we have to, again, carbon has to make 4 bonds. We can draw out all those hydrogens. But of course, know that this structure is completely appropriate, and all the hydrogens that aren't explicitly drawn are implied. And so that's really kind of the key thing in organic chemistry. So that's just how to write N-hexane. Then we said that we could write all sorts of isomers where you have branching. Oops. So now we have 1, 2, 3, 4, 5, 6. So that's just one other isomer. So we could redraw this. So now we have a carbon in the center there attached to this carbon. And so now you just explicitly draw out all the hydrogens. And so for these geometrical isomers, you notice that they would have the same formula, just different connectivity. So in this case, we have C6H. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this one should be the same. So C6, you can see my 6 carbons. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So same formula, different just physical connectivity. So kind of the next thing to be aware of is, well, how many bonds does each thing make? And this goes back to our Lewis dot structures in a lot of ways. So let's recall Lewis dot. So hydrogen, that was pretty simple. So of course, this is our first element, has 1 electron. But we know from this, so right, hydrogen wants to satisfy duet rule. So we remember that. So it's only missing 1 electron because it just has that 1 s orbital to fill. And so this means that hydrogen only makes 1 bond. And so that makes sense. we see that just bonding singly to carbon. Welcome, welcome. Just let me know if you have questions in the chat. So now looking at carbon, so if we remember its Lewis dot structure, we usually draw the Lewis dot structure of carbon like this. So we mentioned it's kind of one of those exceptions, and those electrons can fill up one on each side, and that's due to that hybridization. So sp3 hybridize, and so we know carbon has to make 4 bonds. So now let's look at the Lewis dot structure of nitrogen. So how many bonds do you think that would make? Let's first start. So we have nitrogen, group 5, so 5 valence electrons. So this is showing, so nitrogen has 1 lone pair here, so it's not really interested in making a bond that way, but it does tend to make 3 bonds since it has this 1 lone electron on each side. And so we find that's the case. So nitrogen wants to make 3 bonds. So that could be to carbon, to itself, to combination. Usually see like nitrogen, it could make bonds to hydrogen like in ammonia. Or you could also have, you know, some sort of nitrogen, carbon bond. So whatever attached to it, or oxygen. So looking at oxygen, its Lewis dot structure. So it has 6 valence electrons. I'm just going to fill those in. And so that gives us 2 lone pairs. And then we have these 2 lone electrons there. So that means that oxygen likes to make 2 bonds. You see this a lot with carbon. So like carbonyls. And then R just means, you know, some sort of the rest of the substituents. And then halogens, so our halogens usually just symbolize it with X in organic chemistry. And so our halogens, right, so that's fluorine, chlorine, bromine, iodine. All of these have, you know, the same pattern of Lewis dot structure. So let's just look at chlorine. We have 7 valence electrons. So I'm going to fill that in. So notice we have just 1 lone electron there. So the halogens tend to make 1 bond to satisfy the octet rule. So any questions about that so far? So these are just, you know, general rules to kind of help you see how these structures are going to go together, what kind of bonds to expect. But all this should be also building upon these Lewis dot structures. So that's why they were so important first quarter, because now we're understanding how many electrons they have, how many they're bringing, you know, to the party, and then how many bonds they're going to want to make. So let's look at our shapes now of our organic molecules. And so let me link to something. This is going to be excessive, but so I'll post a link to this. But this is essentially what we're going to cover right now. And this is just like a cheat sheet to geometries, but we'll go over kind of what you need to know. So I'll put this as a link so you can reference it later to get kind of the complete story. But let's focus on kind of what we're going to see. And so the way things are classified, and if we go back to that page here, so basically we have what's called, everything's grouped by these electron pairs. So these electron pairs are how many things are attached to it. So that's either lone pairs or substituents. Then you see first which, kind of big group it falls under. And then you look, if those three substituents are all atoms, this is a geometry. If one of them is a lone pair, this is the geometry. And so this whole chart breaks everything down. But right now we're going to cover kind of what you will see in organic chemistry. This is just a full extensive list. So let's start with our 2 electron group. And so the organic chemistry example that we'll see from this group is CO2. So take 30 seconds, see if you can draw out the Lewis dot structure for CO2, and then we'll go over it. All right, so now we can already start using our principles, and I should have started making a molecule of it, but we know that carbon wants to make 4 bonds, so I'm going to put that kind of in the center. And so that we have kind of 2 things, so, it makes sense. This is all coming together nicely. Carbon wants 4, oxygen each wants 2. There's 2 of them. So boom, I have my 4 bonds. And then if we look at our Lewis dot structure for oxygen, we know that it carries those 2 lone pairs with it. So don't forget to draw those in. Remember the best approach is to always just make sure you keep track of your total number of electrons. So write total electrons, and that's valence electrons, so that's 4 from carbon plus 6 from each oxygen. So we get 12 plus 4, so that's 16 total electrons. And so we can tell kind of from our structure that our geometry is linear, and this also kind of matches with our cheat sheet. But let's build out our structure so it makes sense. So I have my carbon with my 2 kind of double bond representations. So these red balls represent oxygen. So I'm just getting some oxygen. And so if you notice with these red balls, they tend to only have 2 holes, since we said oxygen only makes 2 bonds. So they're kind of primed for that. So there's our now representation of it, so you can see that it is linear. So I'm trying to point it down so the camera can see. So our linear shape there. And so the other thing, when you're reading this chart, don't let the double bonds confuse you. All you care about is how many things is it attached to. So again, it's attached to 2 things. That brought us to our chart here. And then of course linear, that means that this angle is going to be 180. It's kind of self-explanatory. So that finishes up electron group 2. So let's look at our 3 electron group. So this one, you'll see, I'm trying to think of a good example compound. So these 3 electron group, kind of abbreviated this AX3, meaning you have 1 center atom plus 3 substituents. So this could be BF3. It's kind of your classic example in this case. Another example would be like the acetone shape. So let's look at both of those. So both of those kind of follow the same principle. So you have an atom in the center connected to 3 substituents. And so in both cases, I'm just filling in our total number of electrons. So in this carbon case, right, again, we don't care that it's a double bond. It's still that correct geometry. And so in this case, let's go back. So this electron group 2, so it's a center atom with 2 things attached to it. And so because it has 2 substituents, that helps us remember that it's sp hybridized. So that means 1s plus 1p came together to give you this bonding orbital there. So now that's in phase to bond with my oxygen. So now with my 3 electron group, it's called sp2 hybridized. So now we have s plus 2 p's coming together. So in this case, probably we'll just say py and px. We're saying pz is coming in and out of the plane of the board, but it gives you that kind of 3-lobe looking structure now to bond with those 3 substituents. And so we can look at the geometry. So the geometry here is going to be trigonal planar. So let's go back to our webcam for a second. So I've started with my CO, and now I'm just going to add those 2 hydrogens here. And so you can see that structure laying flat there. So yes, indeed, that is planar. And so it looks like a triangle too. So our geometry is going to be trigonal planar. So go back, geometry, and make sure to write that down of trigonal planar. So now let's skip over to the 4 electron group, because that's really what we're going to be seeing a lot in organic chemistry. And so what's our classic example of our 4-electron group? Of course, now I can't get these bonds off. So our classic example is, of course, methane. So working on my kit. So I'll go back. So there's our methane. Oops, I forgot to put, excuse me there, had the wrong color representation. There we go. So there's our methane. Let's go back to our class here. So 4-electron group. So this could be methane and a whole bunch of other things. But now I'm going to draw it kind of in that 3D structure. So I'll draw carbon. So these two hydrogens are in the plane of the board. This wedge is showing this is coming out of the plane of the board. And this dash is showing going behind the plane of the board. So our geometry for this is tetrahedral. So you could look at your cheat sheet here. So tetrahedral. So this tells you those bond angles too. So 109.5. So all those angles 109.5 and our geometry tetrahedral. So now looking back at our little model, so they're all in the same electron group family. So we're still in the 4-electron group, but now we're doing what's called AX3E. And all this means is that we've replaced one of our substituents now with our lone pairs. And so it might be appropriate too if I change this ball color. So I'm going to go ahead and do that. So our classic example of this is ammonia. So nitrogen is generally represented by these blue ball here. So it has 4 holes. And so I'm going to put my lone pair there. And let me stick in those other hydrogens really quickly. There we go. So now that's ammonia. So you can, again, the whole point is to see that it's in the same electron group. So we haven't really changed much, right? Just swapped a hydrogen out for a lone pair. And so what's the geometry? And you can kind of see that. Trying to show you the 3D. Let's go back to our class. Now I'm just going to draw this out. Lone pair there. And so our geometry is going to be trigonal. And then it kind of looks like a pyramid, right? It's got that kind of triangle. You got the pyramid shape going. And so it's going to be trigonal, pyramidal for its geometry. And so still sp3 hybridized. So the hybridization doesn't change. So that hybridization is dependent on what group it's in. And so next geometry that you'll see in this family is now, so we're going to remove another substituent. So AX2, E2. And so what atom likes to make two bonds? So I'll give you a hint. So remember, we have this red one with two holes there. So we could, I don't know if this makes you feel better or not. So this oxygen does have four holes. So oxygens are red, but I just want to symbolize, I'm using this 4-1. So we could see that, yes, it is indeed part of that same tetrahedral family. So we could say its electron geometry is tetrahedral, right? Same tetrahedral shape. But now what can we say that its geometry is? What does it look like? And so our classic example, if you haven't figured it out, is water here. So we have oxygen. So oxygen likes to make two bonds. Then E2 going to be for those two lone pairs on oxygen. And I go back to that webcam so you can see how that's going to be laid out. But, whoops, smack my mic. Just for clarity, so you can see that that's laying down flat. And so its geometry is going to be bent. So something else that I want to point out is these bond angles are going to change a little bit. So as you remove a substituent and replace it with a lone pair, so that lone pair, it's more repulsive, so it takes up more space. So it's actually kind of pushing down just a little bit more on those hydrogens. So if we look back at our little cheat sheet here, we see that the angle now has decreased to about 107. And so that's the effect of one lone pair, and now two lone pairs bring it down even a little bit further. So now this bond angle is a little bit smaller at 104.5. So they say it's about like a 2-degree effect for every one lone pair, roughly. So now 104.5 degrees, and that was about 107. So some things that you may be asked to do is kind of determine the 3D shape. And let's go on to the next page, actually. So I'm just glancing at my notes as well, seeing what we need to cover. And so this kind of goes along with drawing these molecules. But you want to be able to look at this structure and then interpret, like, what's the geometry at each center? What's going on? What does this mean? And kind of determine the formula. So let's just look at a few bits and pieces here. So I just pulled up Lipitor. If you have a favorite molecule, send it in. I'll throw it up here and we can look at it. And so, I want to emphasize that, again, everything is drawn out explicitly except all those little hydrogens that are not shown. But every other hydrogen, the only hydrogens, let me rephrase that. The only hydrogens that are missing are the ones attached to carbon. But all other hydrogens, so if it's a hydrogen attached to an oxygen, that's drawn out. Hydrogen attached to nitrogen, that's all drawn out. And so let's look at this. So one skill that you want to be able to do. We'll just call it, can you fill in the hydrogens? And so this goes back to our principle. Every carbon needs 4 bonds. So if it's not explicitly bonded to 4 things, then those other things must be hydrogens. And so let's look at that together. I'm just going to start on this ring here. So remember, this point is a carbon, this point here. And you could even kind of draw, carbons everywhere. So this might be step 1 for you, is just kind of drawing out, where are my carbons? And so every point here is a carbon. So I'm just filling in all those carbons, carbon, 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 carbon. Okay, finally finished. I'm going to switch colors for this. And so now that we have all our carbons explicitly drawn, let's fill in our hydrogens. So I'll start back at my ring over here. So this carbon, this point here, has 1, 2, 3 bonds. So I know it needs 1 hydrogen. This one has 1, 2, 3. So I need a hydrogen. 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 And so notice this one has 1, 2, 3, 4 bonds. I'm not going to fill anything there. This one has 1, 2, 3, 4 bonds. Don't need to add anything. This carbon should have 3. This one has 1, 2, 3 bonds. So I need 1. CH3. So this one has 2 bonds. So CH2. CH2. This carbon has 1, 2, 3. So I need 1. CH2. 1. CH2, none there. So this has 1, 2, 3, 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Those are all good. 1, 2, 3, 4. And so now I just need to fill in the rest on this ring here. So 1, 2, 3, 4. Don't need any there. All right. Oops. Lost one of my molecules. All right, so that's good. So now let's look at kind of the next analysis we want to be able to do. Is that now that we can, fill in our carbons and hydrogens and know what this means, can we identify geometries? And we can even break it down a little more simply. So I picked a complicated molecule, to kind of scare you. But the point is that any complicated molecule can be broken down. You can understand it. You can analyze it. That's what organic chemists, do. And so let's take a look at these aromatic rings for a second and just, what they look like. What's the geometry going to be? What can we predict? Oops, I keep dropping. Now I've lost 2 balls. So we can draw out this aromatic ring like this. I just want to point out some things. So this ring has resonance structures. So that means it doesn't really matter where we draw the double bonds, because we could shift them over. Gives you the same representation. This is because you have a delocalized aromatic system. So these pi electrons are just delocalized. And sometimes you even just see this representation. And that all means the same thing. And so my next question is, so what's the geometry of this benzene? What's it look like? And so you can answer that. Let me redraw this. So what's our hybridization? What electron group is it in? Just drawing out our hydrogens explicitly. But if we look at one bond here, we look at our carbon, right? We have that it's bonded to three things. So essentially we have carbon bonded to 1, 2, 3 things. So if we have carbon bonded to three things, or anything bonded to three things really, that gives us a trigonal planar geometry at that center. So actually what you find, and so this will hopefully start to make sense. So right, the geometry at each center is trigonal planar. So everything, all right, all this is planar. So you can tell that this would be trigonal planar, this is trigonal planar. And so that means that this whole molecule of benzene then is planar. And so that's true. And so that's really cool that you were able to determine that just by these Lewis dot structures. At least I think that's cool. And I just wanted to pull up benzene so you could see that, yes, it is indeed a planar structure. So now the other thing we can do is we can look at the geometry at all these other centers. So I'll put this kind of part 2 of can you get the geometry at each center? And basically what that means is, can I pick out a carbon? Can you tell me what the geometry is? So let's look at this carbon. So now we have carbon, and don't let this fool you, right? So you can always go back to this drawing here. How many things was it really attached to? So 1, 2, 3, 4 things. And so if we have carbon with 4 things attached to it, that's going to be sp3 hybridized tetrahedral. What about this carbon? How many things is it attached to? What's its geometry? What's its hybridization? So you have carbon there, right, bonded to 1, 2, 3 things. So that's sp2, and that's going to be our trigonal planar again. So now we can tell this part is planar. What about this carbon? What's its geometry? So once again, going to be sp3 tetrahedral. What about these nitrogens? Yeah, let's not look at these nitrogens. Let's see, what about this carbon? So this carbon, 3 things again. So sp3, trigonal planar. So kind of the last things that you want to practice are just these skeletal structures and converting them to kind of full structures and vice versa. So for example, and I'm just looking at one from your book now, cyclooctane. See if I can draw this. So cyclooctane, let me make sure I made 8 points. So 1, 2, 3, 4, 5, 6, 7, 8. So that gives me my 8 carbons, cyclooctane. But this is its skeletal structure. But can you take this and then now draw out explicitly all our carbons? And I'm not the best artist. 1, 2, 3, 4, 5, 6, 7, 8. And then now filling in all our hydrogens. So do we have any questions right now? See, I'm just looking ahead because I think I want to save these functional groups for Wednesday, where we dive into that and we'll look into solubility. That'll help us. So I just want to make sure we're comfortable today kind of interpreting these structures. Drawing them. So make sure you take time to draw them, practice them. Just seeing what else your book has. Here's a good one. Here's a good practice that I see before we kind of leave. So you're ready for these types of problems. So you might see something that'll say, what's wrong with this structure? So I'm going to draw this structure out. So what is wrong with this structure? And so hopefully many of you were screaming internally, but you have this carbon with 1, 2, 3, 4, 5 bonds to it. So this is wrong. Texas carbon. And that's just a joke. So you shouldn't have carbon with 5 bonds to it. So you don't want any Texas carbons. That doesn't make sense. So something is wrong with this structure. So you could do correction. Either get rid of that double bond. So of course we don't know what the structure is really supposed to be, but this is valid. Or we could leave that double bond in and then just have one CH3. And of course we could tell the difference, right? The geometry of this one would be tetrahedral. The geometry of this shape would be trigonal planar. And so that could help you determine. So just be on the lookout for that. Don't make carbons with extra bonds. Just make sure it has 4 bonds. All right, I think we're at a good stopping point for lecture. So again, my emphasis is just practice, practice, practice. I'm available for office hours today or by appointment. I'm very available. I posted my schedule on the 105 resources, so you could check out my schedule. But really, I'm just trying to make myself as available as I can for y'all, because a lot of this is just, you practicing, and maybe you'll see some scenario and have a question about, and I'd be more than happy to answer that. But let's go ahead. We'll end here for today. So we'll pick it up on Wednesday with our functional groups, but just make sure you feel really solid about this. So it's trying to go slow. So make sure you feel solid about the geometries, just how to put things together. And this should be somewhat of a review. But if it's not, set up an appointment, get this down ASAP, because you just want to feel good before you move on to other things. All right, so hang around on stream in case there are any other questions. And again, don't hesitate to email me if you have questions or want to meet individually for an office hours appointment. And then don't forget Lab 1. So I'll see some of you all in person on Wednesday. Otherwise, I will have that video uploaded later today for people to do the lab at home. So have a wonderful Monday, and I'll see y'all on Wednesday.